and it's called sign-based derivative filtering for stochastic gradient descent. And to begin with, I want to begin with some motivation, and then there is going to be some introductory experiments, and only then we will reach the actual benefit of our study. So the motivation is that when you train a model using SGD, stochastic gradient descent, the model parameters are updated by the gradient that you compute at each iteration. You have a batch of examples, you compute gradients, you average them, then using this average gradient, you update your model roughly. Okay, there are some improvements, some other modifications, but that's roughly the core of SGD. And the research question is, how informative is this gradient of the mini batch? And in particular, we can ask ourselves, maybe we can speed up the training by better exploitation of the information from the mini batch gradients. And to begin with, who said that we should average the gradients? This is just a funny question that I would like to ask. But in order to perform interesting experiments, I just defined a small synthetic data set, a binary classification data set, where a model needs to classify 100-dimensional vectors. Each vector is drawn at random from one of m Gaussians, and half of those Gaussians are class 1, half of them is class 0. The model needs to learn to separate between those Gaussians, and the higher the m, the harder the task. So we prepared this random synthetic data set, and I just empirically found that 3200 Gaussians is good enough. It's hard enough. I came up with just some random architecture, and this will be my experimental setup. I have some fully connected 3-layer neural network. I have a synthetic data set, and let's see what we can, what observations can we make. So I have a question. Yeah, maybe it will be interesting if you will try to answer it. So what happens if just instead of averaging the gradients in a mini batch, I use median? What will happen? Can you just throw an answer? Do you have any hunch? I have a mini batch of gradients. Instead of averaging them element-wise, I'm doing median. What will happen? Yeah, so that's a peculiar question, but in our case of a binary classification, the median averaging of the median aggregation of gradients will actually stall the training, and the accuracy will reach somewhere around 50%, which is not better than a toss of a coin. And the well-established averaging works well. The model trains. This graph shows you the increase of the training of the accuracy in time of training. And why does this happen? Well, it's because you have a lot of zeros in the mini batch. Every partial derivative of every parameter has many examples that yielded a zero valued derivative for it. And this median picks up on these zeros because you have some positives, some negatives, but you have a lot of zeros. And in fact, if we look at the sparsity, the number of zero-valued partial derivatives yielded by the median aggregation approach, it's almost 100% zero values. Whereas the well-used averaging approach has around 4%, 3% of zeros in it. So it keeps producing non-zero derivatives, which drive the training forward. It causes updates in the model, and we're getting somewhere. We're not stuck at 50%. So this is one interesting observation. So because of this balance of positives or negatives that eventually break the tie around the zero, we really think that it's all about the signs. We want to look at the signs of the derivatives, and we can look at them in two ways. So calligraphic L of weights and batch means that this is the average loss value of the model W averaged across the examples in mini batch B. We can look at changes in time, namely, we look at the partial derivative of a loss function with respect to one parameter at the current batch, and we look at the very same derivative but in the next batch. And if there is a change, this is a change in time. Okay, and this whole discussion about changing in time can lead us to an interesting study of compression of gradients, which is very useful for distributed training, for example. But I'm not gonna deal with this one, but instead I'm gonna do a slightly different sign change observation. I want to look at the I want to look at the sign of a derivative and compare it to the sign of the same partial derivative, but taken across the entire data set. This is sort of gradient descent, not stochastic gradient descent. This is like a gradient descent result, and this is the mini batch stochastic gradient descent. And I want to compare their signs. And if the signs are differ, I call this an exploration, namely, this partial derivatives is rebellious. He wants to go against the gradient descent direction. And if it complies with the sign of the gradient descent, then we call this one an exploitational step. And this is the experiment that I was leading towards. I'm showing you the histogram of the values of the partial derivatives taken in the stochastic gradient descent training, and I show you this histogram, but I also, in every bin, I'm coloring in two different colors. In red, the ones that their corresponding gradient descent full data set derivative is negative, and in green, the derivatives whose corresponding gradient descent derivative is positive. And you can see that roughly half of the derivatives across the mini batches agree, and slightly less than half disagree with the sign of the gradient descent, which in a sense means that stochastic gradient descent updates are very erratic. It's like you do 10 steps forward, 9 steps backwards all the time. And we, of course, know that this is not entirely true, because this erratic behavior helps in getting out of local minima, and it helps actually in this whole hard task of exploring, of optimizing a nonlinear optimization target. But we still want to investigate this peculiar situation where really only a little bit more than half of the derivatives comply with the sign of the gradient descent. And our idea is to try to come up with an experimental approach which tries to weight, to rescale the derivatives differently, whether they are exploratory or exploitational. And we call this algorithm derivative filtering. And we use basically two main parameters, design parameters, alpha and beta. With alpha, I'm about to amplify the exploitational derivatives, the ones that agree in terms of sign with the gradient descent sign. And with beta, I will amplify differently the disagreeing ones, the ones that we call exploratory. So I'm going to hold the history of gradients. This is going to be a moving average of the gradients, but I initialize it to be just an average gradient across the entire data set. I also maintain momentum as it's commonly used in momentum stochastic gradient descent. And I'm starting my training loop where I go from epoch 0 to the end. And for every epoch, I'm drawing a mini batch at random without replacement. And I'm starting this iteration by computing the row gradient. This is just the average gradient. Okay, I'm not using this median. Okay, in case you are confused, I'm using the plain and popular averaging of the gradients across the mini batch. I then compute a binary map of sign correspondence. So whenever this row gradient agrees with the gradient descent history gradient, you have a 1. If if the gradient descent partial derivative does not agree with the gradient descent, then you have a 0 in this corresponding location. Then I use this map to scale by alpha the exploitational, the agreeing one, and by beta the disagreeing one, the explorational. Now I have this GT, the scaled gradient. And using this scaled gradient, I update the momentum and I update the weights using this momentum. But this is like a standard Nesterov update step of momentum stochastic gradient descent. Finally, I'm using some gamma factor, discount factor, in order to maintain a moving average of the history of the gradients. And this provides me this estimation of gradient descent direction. So what you need to take from here is that alpha and beta are the knobs using which I can increase or decrease the impact of the exploratory and the exploitational derivatives on the training process. And graphically, for those of you who lost me, all I did is just computing a gradient, comparing its sign to the history gradient, and if it agreed, I amplified it by alpha, otherwise by beta. So let's see how does this work. What the results on the CFAR 10 and CFAR 100 datasets. In these plots, I'm showing you in the x-axis we have the training epoch, and y-axis we have the validation set accuracy. And the different colors stand for the different alpha to beta ratios, which are exploitation divided by exploration amplification factors. So it looks like actually the stochastic gradient descent benefits from alpha to beta equals 2. So we need to twice to amplify the exploitation to exploration ratio. And it actually increases a little bit the final result of the accuracy. But also, in next slide, now I'm showing you the training accuracy, which actually drops. So higher exploitation leads to a higher test accuracy and lower training accuracy, which means that we have less overfitting using this exploitation amplification. Finally, in this slide, I'm showing you the impact of the discount factor, this gamma, that the higher the gamma, the more weight I'm giving to the old history of gradients. And of course, you can argue and say that gamma should be really related to the number of mini batches that I have. And it really is. If you have really a lot of mini batches, then of course you need a high discount factor. Yeah, so we saw that whenever you reach towards 1, if your gamma is 0.99, you have a much better performance in terms of test accuracy reached. Now I'm going to show you this table. I actually performed this experiment 10 times for every model, and I'm presenting here the average test accuracy with our approach and without our approach, and the standard deviation taken across all of these repetitions. So we can improve somewhere between 0.5% to 3.5% in test accuracy simply by amplifying the exploitation compared to exploration derivatives. it's worth mentioning that we also considered an interesting approach. We considered many approaches, yeah, but one worth mentioning, we call it the angular approach, where instead of just comparing element-wise only the signs of the derivatives, we also looked at the angle between the current gradient and the history gradient, and according to this angle we made decisions regarding the amplification of the derivatives. For example, if there is more than 90 degrees difference between those gradients, we would like only to apply beta factors for all the derivatives. And we also investigated different theta dependent alpha factors. So you want to amplify the exploitational derivatives by something that is correlated with the global deviation of the gradients. And all of these approaches only came close to this simple approach of just local sign check. So I'm not bothering you with the results on this approach, but it's worth mentioning. So to conclude this work, we propose the training routine that builds up on the stochastic gradient descent, and it allows you to control the exploratory steps of the mini batch SGT. We did it by reweighting the exploratory versus the exploitational optimization steps. And we showed a higher accuracy and reduced overfitting based on ResNet architecture in image classification tasks.